All right, imagine this scenario. You're sitting there, high stakes, system design interview, you've got the whiteboard marker, you're feeling pretty good, sketching out this brilliant architecture, right,
Yeah.
for a new service. Super scalable.
Yeah, you got it all mapped out.
Exactly. All the pieces, databases, APIs, the queues, load balancers, everything looks just perfect on the whiteboard.
Mm-hmm. The happy path.
The happy path, precisely. Then the interviewer, they kind of lean forward, a bit of a glint in their eye, and they ask, that looks solid, but tell me, how exactly does your system handle partial failures?
Ah, yes. The question.
That right there is often the moment of truth. It's the question that really separates the solid senior engineers from, well, those who've only thought about things working perfectly.
It's absolutely a classic differentiator, isn't it? Because look, understanding distributed systems and especially, their inherent messiness, how to gracefully handle the failures that will happen, it's not just a nice to have anymore. It's completely non-negotiable for senior roles, particularly in system design interviews. It actually requires a fundamental shift in how you think. You're moving away from that predictable world, the sort of idealized single node system where things basically work or they just crash completely.
Right, the simple life.
And stepping into the chaotic, sometimes beautiful, often frustrating reality of distributed computing. It's a different game.
Exactly. And that right there, that's our mission today. We're going to dive deep, equip you with the knowledge, the practical examples, and hopefully the confidence to absolutely nail those crucial questions about fault tolerance, resilience, all that good stuff. So this deep dive, we'll explore the really fundamental differences between how single-node systems and distributed systems behave when things start failing. We're going to contrast philosophies like, supercomputing versus modern cloud computing.
Big difference there.
Huge. And then maybe most importantly, we'll get into the kind of counterintuitive ways you can build incredibly reliable systems using parts that are, inherently unreliable by themselves.
Yeah, building castles on sand almost.
Kind of. Yeah. We'll dive into key design patterns, think circuit breakers, bulkheads, walk through some real-world failure scenarios, stuff that happens all the time, and show you how to talk about your solutions in a way that really impresses an interviewer. This isn't just theory, it's intensely practical, designed to give you that edge.
Okay, so let's start unpacking this. First core concept. The big difference between partial failures and total failures. Now, when you write a program, say for a single computer desktop app server process on one box, it generally behaves very predictably.
Right.
It either works exactly like you intended, processes data, gives correct results, or it completely crashes. Think kernel panic on Linux, or the classic blue screen of death on Windows.
The BSOD. Good times.
And this isn't an accident, It's actually a deliberate design choice way down low in how computers are architected.
That's a really interesting point. It might sound a bit weird, but if there's some kind of internal fault, we actually prefer the computer to just crash completely.
Yeah.
Rather than giving us subtly wrong data or confusing results or, corrupted stuff.
Why is that, though?
Well, because wrong results are just so much harder to debug, right, and deal with compared to a straightforward crash. A crash is loud, it screams, hey, I failed, but subtly wrong data.
Yeah.
That can silently creep through your system and corrupt everything.
Yeah, silent killers.
Totally. So at a low level, computers are designed to kind of hide the messy, unreliable physical world of their hardware. They present this idealized, almost mathematically perfect model to the software. Like a CPU instruction that's your central processing unit, it always does the same thing with the same inputs. You write data to memory, to disk, you expect it to stay intact. It doesn't just randomly flip bits or vanish.
Right, it's this foundational promise of always correct computation. Goes way back.
Exactly. Foundational promise.
But, and here's the big but, when you're writing software that runs across several different computers, connected by a network, which is, the definition of a distributed system, that whole idealized model, it just goes right out the window.
Yeah, forget about it.
In distributed systems, we just cannot hide from the messy, unpredictable physical reality anymore. And in that physical world, a remarkably wide range of things can and absolutely do go wrong. And we call this a partial failure.
Okay, partial failure. So what does that mean exactly?
It means some parts of the system are broken, maybe in really unpredictable ways, while other parts are ticking along just fine. It's not an all-or-nothing situation anymore. Some bits work, some bits don't.
And this leads us straight into this idea of non-determinism. That's non-determinism. Because really, when you try to do anything involving multiple nodes in the network, the outcome well, it might work perfectly fine. Or
It might.
fail in a completely unpredictable way.
Yeah, you just don't know.
Even something as simple as sending a message across a network that's non-deterministic. You send it off, but you might not know if it was received, or if it was processed, or if the reply will ever come back, or even how long it's going to take.
Right. It might get there, might be delayed, might get duplicated for some weird reason, might just vanish into the ether. Dropped entirely.
Exactly. And this inherent unpredictability, combined with the constant possibility of these partial failures, that's precisely what makes distributed systems so incredibly challenging, compared to single node stuff anyway. It's not about if something fails, it's always when and how, and often in really subtle, unexpected ways.
And to make this really concrete, think about some of the stories from folks like Coda Hale. He's a well-known engineer, shared some pretty wild infrastructure failure tales.
Oh yeah. Like what?
Well, he talks about things like long-lived network partitions happening inside a single data center, a DC, where some racks just can't talk to others for hours.
Wow. Inside one building.
Yeah. He's seen PDU failures, that's power distribution unit, where boom, half a rack just loses power. Critical network switch failures, accidental power cycles of whole racks, oops. Whole DC backbone network failures, complete data center power outages from problems way upstream. And get this, even a story about a hypoglycemic driver smashing his pickup truck into a data center's HVAC system.
No way. The air conditioning.
Yep, the HVAC crippled the cooling for thousands of servers. The point is, these aren't like rare textbook edge cases. This is the real messy world of operating large systems. You have to assume this stuff happens.
And that's exactly what interviewers want to hear you discuss. When you get that system design question, a really common follow-up is going to be something like, okay, what's the fundamental difference between partial failure and total failure? And critically, how are you handling partial failures in your design?
All right. Because the red flag.
The huge red flag is if you ignore this stuff. Or worse, just assume it won't happen. Saying, oh, my system won't fail. That's interview over pretty much.
Yeah, you're done.
Strong candidates, the senior folks, they embrace this chaos. They don't just acknowledge it. They lay out concrete, well-thought-out strategies, how they anticipate it, how they mitigate it. They get that designing for failure is just as important as designing for success.
Absolutely. So, okay, we understand failure now, at least the messy kind. Let's pivot a bit and talk about two really different philosophies for dealing with reliability when you're operating at scale. Cloud computing versus supercomputing.
Ah, okay. Two ends of the spectrum.
Pretty much. They represent two very different approaches to reliability in large systems. So at one end, you've got high-performance computing, HPC. Think massive supercomputers, thousands of CPUs, often used for really heavy-duty scientific stuff, weather forecasting, molecular dynamics, physics simulations.
Right, your big number crunchers.
Exactly. And their approach to faults, it's pretty straightforward, almost brutal. In a typical supercomputer setup, a long-running job will periodically checkpoint its state, saves everything to durable storage, maybe every few hours, depends on the job.
Okay, like a save point in a game.
Kind of. Now, if one node fails just one computer in that massive cluster while it's doing a huge calculation, the most common solution is just stop the entire cluster workload.
Stop everything, just for one node.
Yep. All ongoing calculations just halt. Then, after they figure out which node failed, fix it or replace it, they restart the entire computation from the last saved checkpoint.
Wow.
So essentially, a supercomputer deals with a partial failure, one node failing by escalating it into a total failure for the whole cluster. It's like that single node kernel panic, but scaled way up. If any part breaks, the whole thing crashes and restarts.
Okay, it's decisive.
Now contrast that sharply with cloud computing, which is, the other extreme, and it underpins pretty much all the internet services we use every day. Cloud computing isn't just about renting servers, it's fundamentally a different philosophy of handling faults, often called graceful degradation.
Graceful degradation, okay.
See, internet applications are typically online apps. They need to serve users, usually with low latency, all the time. Stopping the entire cluster for repairs like HPC does, that's just completely unacceptable for a live service.
Yeah, your users would not be happy.
Exactly. An offline batch job, like that weather simulation, it can tolerate restarts. The scientists aren't sitting there waiting interactively, but your e-commerce site, your streaming service, your social media feed, it absolutely cannot just stop. Users will just go elsewhere.
That's a really critical difference. And I guess it extends down to the hardware they use, too.
Absolutely. Supercomputers often use really specialized, custom-built, super reliable hardware. Nodes might talk via shared memory or RDMA, that's remote direct memory access.
RDMA, that's the super fast memory access thing.
Yeah, lets one computer grab memory from another directly, bypasses the OS, super low latency, high throughput, perfect for those tightly coupled HPC jobs. But cloud services, they're built from commodity machines, standard off-the-shelf servers.
Cheaper, right?
Much cheaper because of massive economies of scale, but they also have inherently higher individual failure rates. So the design philosophy is totally different. You accept they will fail, and you design your software system around that fact. You expect failure.
Okay, so hardware's different. What about the network?
Also quite different. HPC often uses specialized network setups like multi-dimensional meshes or toruses, custom optimized for their specific, often predictable communication patterns. Big data centers in the cloud, though, they mostly rely on standard IP Internet Protocol and Ethernet.
The stuff we all use.
Pretty much. Often arranged in what are called close topologies, that's CLOS. It's a type of multi-stage switching network designed for really high bisection bandwidth.
High bisection bandwidth, meaning
Aiming, it can handle a huge amount of traffic flowing basically anywhere to anywhere within the data center. Great for the unpredictable, bursty traffic you see in general-purpose cloud workloads. It's built for flexibility and scale, even if it adds complexity for fault tolerance compared to those specialized HPC networks.
And I guess the sheer scale of cloud makes failures even more likely.
Exponentially more likely, yeah. The larger a system gets, tens of thousands, hundreds of thousands of nodes, the higher the probability that something is always broken somewhere. It's not just likely, it's practically guaranteed.
So if your plan is give up when something breaks,
a large cloud system would spend more time recovering from faults than actually doing useful work. It'd just be constantly crashing and restarting. Total non-starter.
right, which leads to some big operational benefits for the cloud approach, I imagine.
Huge benefits. If your system can tolerate failed nodes and just keep working around them, that's massive for operations and maintenance. Think about rolling upgrades.
Oh yeah, deploying code without downtime.
Exactly. Instead of taking the whole service down, you restart one node at a time. The service keeps running, users don't notice. Or in the cloud, if a virtual machine, a VM, is acting flaky or slow, you often just kill it.
Just shoot it.
Yep. Terminate it, request a new one from the cloud provider, hope the new instance is better. This becomes just a normal, routine operational practice. It's built into how you manage cloud systems. Treat servers like cattle, not pets.
And then there's the whole geographic distribution angle, right?
Right.
Cloud services aren't usually just in one place.
Good point. Modern cloud stuff often deploys services across multiple geographic regions, sometimes continents apart. Why? To get closer to users, reduce latency, and for disaster recovery. But that means your communication is often going over the public internet.
Which is not exactly reliable.
Far from it. It's slower, less reliable, much more unpredictable than the local specialized networks HPC assumes. So yeah, in an interview, you might get asked things like, how would you design for high availability versus, say, extreme high performance?
Okay.
Or when would you choose fail fast versus graceful degradation in your design, and why? Your answer needs to hit on these trade-offs, hardware, network, and most importantly, the specific use case and what it really needs in terms of availability. There's no single right answer.
Makes sense. So this all leads to this kind of mind-bending idea, building reliable systems from unreliable parts.
Exactly. This is really the art of fault tolerance. It sounds counterintuitive, right? How can a system be more reliable than its weakest link?
Yeah.
But it's actually an old idea in computing, in engineering generally.
Okay. How does that work in practice?
Well, the magic isn't just layering reliability on top later. It's about designing for failure at every single layer of your system. Think of it like building a ship with bulkheads. You know, compartments might flood, but the bulkheads stop the whole ship from sinking. The system survives even if parts fail.
Right. Contain the blast radius.
Precisely.
Okay. Concrete extension.
Sure. Think about error correcting codes. These are amazing. They let you send digital data accurately, even over channels that mess up bits sometimes, like noise on a radio signal, interference, even cosmic rays, flipping bits in RAM.
Right. The channel's unreliable.
Totally. But by adding some redundant information, using clever math, you can detect and often correct those errors. So you build super reliable data transmission on top of an unreliable physical layer.
Cool.
Any others? The classic, maybe most common example, TCP over IP.
Ah, the internet's workhorse.
Exactly. TCP is transmission control protocol, IP is internet protocol. Now, IP itself, Notoriously unreliable. You send an IP packet, there's zero guarantee it arrives, or arrives in order, or only arrives once.
It can do what? Drop packets?
Yep. Drop them, delay them, duplicate them, reorder them. It's chaos down there. But TCP builds a reliable transport layer right on top of that mess.
How?
It uses mechanisms like sequence numbers for packets, acknowledgements, ACKs to confirm packets were received, and retransmission timers. If TCP sends a packet and doesn't get an ACK back within a certain time, it just assumes it was lost and sends it again. It throws away duplicates, puts packets back in the right order using the sequence numbers, even manages flow control so a fast sender doesn't overwhelm a slow receiver.
Wow. So it's basically cleaning up IP's mess.
Pretty much. It's a perfect, everyday example of building robust reliability from an inherently unreliable base.
Okay, so these higher level systems, they can hide the messiness underneath pretty
Yeah.
well, but there are limits.
Oh, absolutely. There's always a practical limit. Error correcting codes, for instance, they can handle a certain number of errors. But if your signal is just completely drowned in noise, you can't magically pull the data out.
Right.
Similarly, TCP can hide packet loss and reordering, but it can't magically make a slow network fast. If your connection is genuinely sluggish, TCP will keep retrying, sure, but the latency isn't going away. You have to understand those limits and design within them.
Which brings us back to designing for faults.
Exactly. It's absolutely critical. You have to build fault tolerance mechanisms right into your software design right from the start. Assuming faults are rare and just hoping for the best, that's just unwise in distributed systems.
So what's the mindset then?
You need what people often call suspicion, pessimism, and paranoia. Sounds negative, but it's productive. It means you have to consider a huge range of possible faults, even the weird ones you think are unlikely. What if the clock on one server goes completely haywire? What if a service you depend on just hangs forever?
And then you have to test for that stuff.
Yes. Crucially, you need to artificially create these situations in your testing environments. This is where practices like chaos engineering come in. Deliberately break things in controlled ways to see how your system really behaves and find those hidden weaknesses. Don't wait for production to teach you these lessons.
Right. So in an interview, you might get asked something like, how do you get 99.99% uptime when your individual components might fail 1% of the time?
Exactly. Or just walk me through your fault tolerance strategy for this service.
And a strong answer isn't just listing concepts.
No, definitely not. It's about specific, real-world failure scenarios and concrete, actionable solutions. Show you've actually thought through the messy details. That shows you're not just repeating stuff from a book, you understand the actual engineering challenges.
Okay, let's get into the toolkit then. What are the specific design patterns we use for resilience?
All right, the patterns. These are your bread and butter for system design interviews when talking fault tolerance. A huge one, absolutely essential to know, is the circuit breaker pattern.
Like in my house.
It's exactly like that. If there's an electrical overload, the breaker trips, cuts the power, prevents a fire or damage. In software, it's similar. If a service you're calling starts failing too much, maybe timing out, throwing errors above a certain threshold, say 50% failures,
Okay.
the circuit breaker trips or opens. It then immediately stops all further calls to that failing service for a set period.
Why? Why stop calling?
To prevent cascading failures, if you just keep hammering a service that's already struggling, you might overload it completely. Worse, your service might get bogged down waiting for responses, consuming threads or resources, which then impacts its callers, and boom, the whole system can domino down.
Okay. So it protects the callers and gives the failing service a break.
Precisely. After a timeout, the breaker might go into a half-open state. It lets just a few test requests through. If they succeed, great, the breaker closes, and normal traffic resumes. If they fail, nope, it stays open, continues blocking calls.
Clever. Okay, what else is in the toolkit?
Bulkheads. Think about a ship again. Watertight compartments, right? If one gets breached, the bulkheads stop the water flooding the whole ship.
Right, isolates the damage.
Exactly. In software, bulkheads isolate critical resources or services. You prevent a failure or slowdown in one part from sinking the whole application. For instance, you might limit the number of threads or database connections specifically allocated for calls to a particular, maybe less reliable external service.
So if that external service gets slow,
It only consumes those few dedicated threads or connections. It doesn't exhaust your main application's thread pool or connection pool, which would otherwise starve other healthy parts of your system. It's resource partitioning to prevent one problem spot from causing a total meltdown.
makes sense. And then the basics, timeouts and retries.
absolutely fundamental. You can't do distributed systems without them. A timeout is just setting a limit. How long are you willing to wait for a response from a network call before giving up and assuming it failed?
Okay. And if it times out, you retry.
Often, yes. But simple, immediate retries can be dangerous. You can easily hammer a struggling service even harder. So usually implement exponential backoff with retries.
Meaning wait longer each time?
Yep, wait 1 second, then maybe 2, then 4, then 8. Gives the service breathing room. And you should also add jitter, a little bit of random delay to the backoff intervals.
Jitter.
Yeah.
Why?
To prevent the thundering herd problem. If a service hiccups and recovers, you don't want thousands of clients all retrying at the exact same millisecond when their backoff timers expire simultaneously. Jitter spreads out the retries.
Ah, okay. Smart.
And crucially, any operation you retry must be idempotent.
Idempotent, meaning you can do it multiple times and get the same result as doing it once.
Exactly. Deleting a user, usually idempotent. Deleting it twice is the same as deleting it once. Charging a credit card. Definitely not idempotent. You retry that, you might double charge someone. Big problem.
Right. Got to be careful with retries. Okay. What else?
Well, load balancing and failover strategies are key. Load balancers spread traffic across multiple instances of your service. That's basic redundancy, but they also work with health checks.
Checking if the instances are actually working.
Yep. The load balancer constantly runs health checks, maybe hitting a health endpoint, maybe checking database connectivity. If an instance fails its health check, the load balancer automatically stops sending traffic to it, directing requests only to the healthy ones. That's failover. Proactive detection is the goal, so you route around problems before users notice.
Okay, those are some concrete patterns. What about the big picture trade-offs? CAP theorem comes up a lot.
It does. The CAP theorem is a really important conceptual framework. It basically says that in a distributed system, when you have a network partition, meaning some nodes can't talk to others, you have to choose between consistency and availability.
Consistency meaning everyone sees the same data at the same time.
Right. Strong consistency. And availability meaning the system stays up and responsive, even if parts are disconnected.
Yeah. So CAP says you can't have both C and A if P partition happens.
Exactly. During a partition, you have to pick one. Do you prioritize ensuring every node has the absolute latest synchronized data consistency, even if it means some nodes have to stop responding or return errors? Or do you prioritize keeping the service operational for users of availability, even if it means some nodes might temporarily serve slightly stale or inconsistent data?
And that's not just a tech decision.
Not at all. It's a fundamental business decision. What matters more right now in this failure scenario? Perfect data sync or keeping the lights on for users? It really depends on the application.
Which leads right into consistency models, I guess.
Absolutely. You need to know the difference. Strong consistency. Every read gets the absolute latest confirmed right, like a traditional database transaction. Essential for things like banking, maybe inventory management and e-commerce. You can't sell the same item twice. Then there's eventual consistency. This means if you stop making updates, eventually all reads will return the last updated value. There might be a short lag, some temporary inconsistency, but it converges. Think distributed databases like DynamoDB or Cassandra. Maybe okay for social media feeds, user profiles. We're seeing the absolute latest update fractions of a second later isn't critical. You trade some consistency for better availability and often lower latency.
And weak consistency.
Weak consistency basically offers very few guarantees. Reads might get old data, maybe even out-of-order data, with no promise it will ever catch up. Much less common for user-facing data, but might be okay for things like analytics logging, where some loss or reordering is tolerable for performance.
Okay. And for availability, you mentioned active, passive, and active.
Right. Broad patterns. Active, passive. You have a primary handling all traffic and a standby that's ready to take over if the primary fails. Simpler for consistency, but failover takes time. That's your recovery time objective, RTO.
And active.
Active. Multiple servers or even whole data centers are handling traffic simultaneously. Better throughput, usually better availability during failures, lower RTO because traffic can just instantly go to other active instances, but much more complex, especially keeping data consistent across all those active sites.
Lots of trade-offs there, and always balancing performance versus reliability too, right?
Always. How fast does it need to be versus how resilient? When is it okay to potentially lose a tiny bit of data maybe those analytics logs again, versus when is data loss absolutely unacceptable, financial records, medical data. And remember, redundancy and replication, they aren't free. They add latency, CPU overhead, storage costs, operational complexity. You're always making choices.
So interviewers will definitely probe on this. Questions like, walk me through fault detection and recovery for a high availability system, or how do you handle the C versus A trade-off in your payment system?
Yep. Or when would you pick eventual consistency for user profiles and what are the implications?
And the key is always,
Ask clarifying questions first. What are the specific availability targets? 99.9%. 5 nines. 99.999%. Because those extra nines dramatically change the design, the cost, the trade-offs you need to make. Don't just jump into a solution without knowing the requirements.
absolutely critical. Okay, let's go deeper into the really gnarly stuff. Network and infrastructure challenges, where things get really messy.
Right. A big one, trips up a lot of people, is network partitions. We mentioned CAP theorem relies on P for partition. This is where nodes in your system can talk to others within their group, but the groups can't talk to each other, like two islands suddenly forming.
What causes that? Router failures.
Could be router failures, could be backbone issues, BGP routing problems, even just a misconfigured firewall accidentally blocking traffic between parts of your system.
And this leads to the dreaded
Split brain problem. This is nasty. It happens when those isolated partitions, because they can't talk to each other, both think they are in charge. They both think they're the primary or the leader. Yeah. Imagine two halves of a database cluster, both accepting rights independently because they think the other half is dead. When the network partition finally heals, you've got two different versions of the truth, two divergent data sets. Reconciling that, it's an absolute nightmare. Often involves manual intervention, potential data loss.
Yikes. So how do you prevent split brain?
This is where quorum systems are vital. They work by requiring a majority of nodes in the cluster to agree before certain critical actions can happen, like electing a new leader or committing a right. For example, in a 5-node cluster, you might require a quorum of 3 nodes to vote for a new leader.
So even if the network splits 2 and 3.
Only the partition with 3 nodes, the majority, can elect a leader. The partition with 2 nodes can't reach quorum, so it can't elect its own leader. This ensures only one leader can exist at any time, preventing split brain. Algorithms like Paxos and Raft are fundamentally designed to solve this consensus problem safely, even with partitions.
Okay, quorums are key. What about bigger failures, like a whole data center going dark?
Yeah, data center failures and disaster recovery, DR. You have to plan for this. Power loss, major network outage, physical damage, like that HVAC incident.
Yeah.
What's your immediate response?
Routing traffic away, right? DNS changes.
Exactly. Intelligent traffic routing, often using DNS or maybe BGP Anycast, to get users pointed to your healthy data centers quickly. But that's just step one. You need robust strategies for data consistency across the remaining DCs. How do you ensure no transactions were lost during the failover? What's your recovery point objective, your RPO, the max data loss you can tolerate? Is it 0? Near 0.
Yeah, to keep the site up, even if it's maybe a bit slower.
Right. Maintain user experience, even with potentially degraded performance temporarily. And then there's the recovery plan. Bringing the failed DC back online isn't just flipping a switch. It involves careful data reconciliation, making sure everything is consistent again across all sites. This needs detailed runbooks and regular DR drills. You have to practice this stuff.
And as systems get bigger, failures just happen more often, right? Scaling challenges.
Definitely. Scaling challenges and bottlenecks are tightly linked to fault tolerance. A design that's fine with 10 nodes might hit a hidden single point of failure or a bottleneck at 1,000 nodes. Network latency between nodes might suddenly become a killer. A rare bug might become frequent. So your scaling strategy must account for failure becoming more common and potentially more severe as you grow.
And if you're global, geographic distribution adds more pain.
Oh yeah. Latency between regions becomes a huge factor, makes synchronous operations really hard or impossible. Data replication gets way more complex, balancing consistency, performance, cost, plus legal stuff like data residency rules in different countries. And your network is now the public internet with all its inherent unreliability. You really have to embrace asynchronous patterns and eventual consistency much more when you go global.
And none of this works if you can't see what's happening. Monitoring and observability.
Absolutely non-negotiable. You need robust tools and practices. If you can't see inside your complex distributed system metrics, logs, traces, you simply cannot operate it reliably, let alone fix it when it breaks. You need dashboards, alerts, structured logging for digging into problems, distributed tracing to follow requests across services. It's your eyes and ears.
So an interviewer might hit you with, how do you handle a complete AWS region outage?
Classic question. Or design a system spanning multiple geographic regions, considering partitions and failures. They want to see if you understand the whole stack of challenges, from network protocols up to disaster recovery strategy and observability.
Okay, theory is great, patterns are great. Let's put it all together. Interview simulation time. Walk me through answering a really common practical question.
Sounds good. Let's do it. Here's the scenario, super common for senior roles. Your e-commerce platform runs on about 1,000 servers, spread across 3 distinct data centers in different geographic regions. Suddenly, one of those data centers completely loses power. Total blackout. How do you design your system to handle this gracefully, minimizing the impact on your users?
Okay, classic. So first thing I do as the interviewee, requirements gathering. I need to clarify. Okay, what are the specific availability goals here? Are we talking 99.9% uptime? Or is it higher, like 99.99%, maybe even 5 nines? What's the target recovery time objective, the RTO? How fast do we need to recover? Seconds, minutes. And the recovery point objective, RPO, how much data, if any, can we afford to lose? 0 data loss.
Excellent start. Always clarify requirements. Let's assume for this e-commerce site they want high availability, say 99.99%, and a low RTORPO. They want quick recovery and basically 0 data loss. So given that, how do you approach the high-level architecture?
All right, for 3 DCs, low RTOR/RPO, I'm immediately thinking active. Active across all 3 regions. Not active-passive. All 3 data centers are serving live traffic. This helps with load distribution and gives us instant failover capacity.
Okay, active. How do you handle the data?
Data is key. I'd use robust cross-region asynchronous replication for most data product catalogs, user sessions, maybe recommendations. For the really critical stuff, like the payment processing database or maybe inventory if latency allows, I might consider synchronous replication between at least 2 regions to guarantee 0 data loss on commit. But that needs careful evaluation due to latency impact. Each DC needs a full, independent stack, app servers, databases, caches, queues, and crucially, global load balancing. Something like AWS Route 53 using latency or health check-based routing to send users to their nearest healthy DC.
Okay, solid architectural foundation. Now the failure hits. DC number 2 goes dark. Failure mode analysis. How do you detect this and what's the automated recovery process?
Detection needs to be fast and reliable. Our global load balancer, using its health checks, would quickly see that the IPs for services in DC2 are unresponsive. Simultaneously, our independent monitoring systems, Prometheus, Datadog, whatever we use, would be screaming alerts. Network connectivity lost, power metrics flatlined, application health checks failing for everything in DC2.
So detection is multi-pronged. Then what happens?
Automation kicks in. The global traffic router, whether it's DNS-based or a smarter load balancer, automatically reconfigures itself. It stops sending any new traffic to the failed DC2. All user requests now get routed only to the remaining healthy DCs, DC1 and DC3. This DNS or routing change needs to be fast to meet that low RPO. What about data? Any transactions heading to DC2 when it died?
Good question. Inflate rates to DC2 would likely time out. The application layer needs retry logic to then attempt the write against a healthy DC1 or DC3. For reads, they'd just be retried against a healthy DC. We rely on the replication, async for most things, maybe sync for critical parts. Having kept DC1 and DC3 reasonably up to date, they take over handling all new writes and reads. When DC2 eventually comes back online, the replication mechanisms will work to bring its data back into sync before it starts taking traffic again. Okay, sounds plausible. But let's talk trade-off justification. This active-active multi-DC setup isn't cheap or easy. What are the big trade-offs and how do you justify them?
Oh yeah, huge trade-offs. First, cost. Running 3 full active data centers is way more expensive than 1 or 2. Infrastructure, bandwidth, operational staff. It adds up. Second, operational complexity. Managing replication, consistent deployments, monitoring, failover testing across 3 active sites. Much harder than active-passive or single DC. Third, maybe consistency challenges. Depending on the replication strategies, especially with asynchronous replication, there's a potential for brief periods of eventual consistency during failover or partitions. Maybe a user sees slightly stale data for a moment.
So how do you justify that cost and complexity for e-commerce?
For a major e-commerce platform, uptime is money. Every minute the site is down means lost sales, frustrated customers, damage to the brand. So the high cost and complexity of an active multi-DC setup is often viewed as the necessary price for achieving that 99.99% or higher availability. You justify the potential for brief eventual consistency for non-critical data, like browsing history, by arguing it's an acceptable trade-off for keeping the core buying functions highly available. But for payments and inventory, you pay the performance complexity price for strong consistency there, maybe using synchronous replication or specific database techniques.
Makes sense. And finally, what about the people? Operational considerations.
Absolutely critical. Technology alone isn't enough. You need well-documented runbooks, step-by-step procedures for engineers who does what during a DC failure, how to verify recovery, how to bring the failed DC back safely, and you must practice. Regular disaster recovery drills are essential. Simulated DC failure and staging, or even carefully in production, to test the automation, the runbooks, and the team's response under pressure. Find the holes before a real disaster does. And underpinning all of it, comprehensive monitoring and observability across all DCs so you know what's happening.
Great walkthrough. That scenario really helps illustrate how to apply the concepts. It also highlights some common interview pitfalls or red flags. What's the biggest one again?
Number one red flag, completely ignoring failure. Say it won't fail, that's rare, instant fail. Another is being vague. Oh, we'll use the cloud. Which cloud services? How? What are the trade-offs? Be specific. And obviously, designing something with clear single points of failure and not addressing them.
Right. Let's try another quick partial failure scenario, common in microservices interviews. Okay, you have a microservices architecture. Your critical payment service starts having intermittent problems. It's only succeeding, say, 70% of the time. This is causing lots of failed checkouts. How do you design the calling services and the system overall to handle this more gracefully?
Okay, intermittently payment failures. Nasty. First thing that comes to mind, circuit breakers. Every service calling the payment service needs a circuit breaker. If it's failing 30% of the time, that breaker will trip pretty quickly. This stops the upstream services from constantly hammering the struggling payment service and prevents cascading failures. Calls might fail fast instead of timing out, or maybe get queued.
Good start. What else?
Second, retry logic with exponential backoff and jitter. Clients calling payments should retry transient failures, but smartly wait longer between retries, add randomness. Crucially, though, ensure the payment initiation is idempotent if you retry. Third, and really important for user experience, fallback mechanisms. Don't just show a cryptic error.
What kind of fallbacks?
Maybe offer the user an alternative payment method if the primary fails. Or display a clear, "We're having trouble processing payments right now. Please try again in a few minutes" message, prepped with an option to be notified. Maybe even implement a system for safe, asynchronous background retries for certain payment types. Degrade gracefully. You might also use a dead letter queue for payment attempts that fail repeatedly so they aren't lost forever and can be investigated or reprocessed later when the service recovers.
Excellent. Tackling it from multiple angles. Let's revisit that consistency versus availability trade-off. Can you give more specific examples of choosing eventual consistency and how you handle potential conflicts?
Sure. Think about like counts on social media or view counts on a video platform. Does every user everywhere need to see the absolute exact count the instant it changes? Probably not. A slight delay, maybe seeing a count that's a few seconds or even minutes old, is usually fine. Here, eventual consistency wins because you prioritize high availability, the site stays fast and responsive, and scalability over immediate, perfect consistency. Contrast that with, say, transferring funds between bank accounts. Strong consistency is the only option there.
And how do you handle conflicts if updates happen concurrently in an eventually consistent system?
That's where conflict resolution strategies come in. A common one is using version vectors or similar mechanisms like Lamport timestamps or vector clocks to track the causal history of data updates. When conflicting versions are detected, e.g. two users updated the same profile field concurrently while partitioned, the system can use rules like last writer wins or maybe application-specific logic to resolve the conflict or flag it for manual resolution. Alternatively, using quorum reads and writes, like reading from or writing to a majority of replicas, can significantly reduce the window for inconsistency and help prevent reading stale data after a write has been acknowledged by a quorum.
Okay. And finally, that balance of performance versus reliability. When is data loss okay? When is it not? And how does redundancy cost factor in?
It really comes down to the business impact of losing the data versus the cost and complexity of preventing that loss. For ephemeral stuff like maybe temporary user session data, detailed debug logs, real-time analytics pings, Some small amount of loss might be perfectly acceptable if it simplifies the architecture, lowers cost, and improves performance. You might use UDP fire and forget or a message queue configured for performance over guaranteed delivery.
But for the important stuff.
For the critical stuff, financial transactions, customer orders, medical records, core user data loss is usually completely unacceptable, period. So you pay the price for reliability. That means things like synchronous replication across multiple availability zones or even regions, using write-ahead logging in databases, employing robust transactional systems, the overhead higher latency because writes wait for multiple acknowledgments, more CPU, more storage for replicas, higher cloud bills. That's just the cost of ensuring durability and correctness for data you absolutely cannot lose. It's a spectrum, and you choose based on data criticality.
Perfectly put. So wrapping this all up, let's distill the key takeaways for acing those interview questions. To really show you get distributed systems at a senior level, you absolutely need to talk confidently about partial failures being the norm, not the exception. You need to understand non-determinism, the differences between cloud and HPC philosophies, graceful degradation.
Right. And explaining how you build reliable systems from unreliable parts, talking through CIP theorem not just as letters, but its real-world impact, and knowing patterns like circuit breakers, bulkheads, how to handle partitions, split brain. That's crucial.
And it's how you discuss it. Structure your answers. Show you understand failure modes. You have practical ideas. You can clearly articulate trade-offs, cost, complexity, consistency, performance, and you always think about the operational side, monitoring runbooks, testing.
And avoid those red flags. Never ignore failure. Be specific, not vague. Don't design systems with obvious single points of failure. Remember, they're assessing your thinking, your problem solving, how you weigh options, not just if you know a definition.
Exactly. And be ready for questions that probe deeper. How do you test for failures you haven't seen yet? That leads to chaos engineering. What's the difference between fault tolerance and high availability? Fault tolerance enables high availability. How do you balance consistency and performance globally? How do you stop cascading failures? These show senior level thinking.
And the best way to internalize this isn't just memorizing. It's working through examples, scenarios, understanding the why behind the patterns and trade-offs. So the bottom line, distributed systems are messy, failures will happen. The best systems embrace this. They build reliability from unreliability using smart design and thoughtful choices. Getting this mindset, that's your path to senior level success.
So what should you do next? Practice. Simple as that. Actively work through system design problems. Start simpler, maybe designing basic web app failover, redundant file storage. Then ramp up. Draw diagrams. Talk through your reasoning out loud. Explain it to someone, even if it's just your rubber duck. Verbalizing solidifies understanding.
That's right. Practice with real problems. Think about what we talked about today. Challenge your own assumptions. Look at the apps and systems you use every day. How might they handle failures? And here's a final thought to chew on. In distributed systems, real mastery isn't just building things that work perfectly under ideal conditions. It's designing systems that fail gracefully, systems that bend but don't break, systems that recover intelligently. How does embracing that mindset change how you approach every piece of code, every architectural choice you make? Something to think about.
We'll catch you on the next deep dive.